and he struggles to remember the English names of the people he meets. Still, those early days have their joys. Spring arrives with beautiful weather, and for a moment, everything feels full of promise. Ramanujan is simply happy to be in this mathematical heaven, where his ideas no longer draw puzzled looks. Most importantly, he now gets to work closely with Hardy and Littlewood, the two elite mathematicians who sifted through his notes and saw the brilliance within. Ramanujan meets with Hardy and Littlewood several times a week. Hardy is especially eager to dive into Ramanujan's notebooks. So day after day, they sit together, working through those strange but beautiful equations. Now, with no ocean between them, it's finally easier for Ramanujan to explain his ideas. He can show Hardy and Littlewood, face to face, the formulas he spent years developing through tireless effort and isolation. Back in India, Ramanujan was always alone. Just Carr's book, his own notes, and his relentless drive. No one around him truly understood his work. But now he has real companions. Although he is living in an unfamiliar country, their presence more than makes up for it. Most of the time, Ramanujan is tucked away in his or Hardy's room, lost in mathematics. He's rarely seen outside, but when he is, people spot him waddling across the court in slippers. Western shoes are too tight for him. When Hardy studies Ramanujan's notebooks, he's fascinated with his intuitive approach to mathematics. It's nothing like the methods of Cambridge-trained mathematicians. Hardy is especially impressed by Ramanujan's insight into algebraic formulas and into the transformation of infinite series. Some of his results are rediscoveries other mathematicians had found 50 or 100 years before. Ramanujan often found new ways to obtain them, but large parts of his notebooks consist of entirely new formulas. At the time, Hardy and Littlewood are only beginning to scratch the surface of Ramanujan's work, and even decades later, mathematicians will still be wrestling with the depth and mystery of the formulas he left behind. Hardy begins to understand how deeply, almost spiritually, Ramanujan connects with numbers. There is a moment when Hardy visits Ramanujan by cab when he notices a number on it, 1729. When he tells Ramanujan about it, he calls it a rather dull number. Ramanujan, in fact, sees much more in it. But what exactly does he see? We invited Derek over, from our good friends at Veritasium, to help make sense of this.
Ramanujan's immediate response is that 1729 is a fascinating number because it's the smallest number that can be written as the sum of two cubes in two different ways.
Cubic numbers are just one number multiplied by itself 3 times. So you can have 1 cubed, 2 cubed, 3 cubed, and so on. Now you can start adding some of these together. For example, 1 cubed plus 2 cubed equals 9, or 3 cubed plus 4 cubed equals 91. If we list all numbers up to 100, what you find is that most numbers can't be written as the sum of 2 cubes at all. And even if you can only write it in one unique way. The same is true for all numbers up to 500, 1,000, or even 1,500. But that changes at 1729. This is the smallest number that can be written as 1 cubed plus 12 cubed and as 9 cubed plus 10 cubed.
Ramanujan already knew about this number, and he recognized it as soon as Hardy mentioned his taxi. In fact, mathematicians named these taxicab numbers after that very conversation. But Ramanujan's incredible grasp of numbers can perhaps be best seen with what he did with pi.
Pi is the ratio of a circle's circumference to its diameter, but what makes it special is that it has an infinite number of non-repeating digits. For centuries, mathematicians worked on finding better and better ways to write down pi. In the 17th century, the famous German mathematician Gottfried Leibniz wrote down the following formula. His formula uses an infinite sum over n. We can start approximating this by taking the expression and replacing n with 0. Next, we add another term, but now we set n equal to 1. And if you keep doing this, you get closer and closer to the true value. If we broke it down and rearranged to find pi, the result would look something like this. Theoretically, if we repeated this process all the way from 0 to infinity, the answer would be exactly pi.
But of course, writing down an infinite number of terms is impossible. We have to stop somewhere, and that means our answer will just be an approximation. The more terms we add, the better the estimate.
We can see this on a graph. For each additional term, the result of the Leibniz formula bounces around, but it slowly gets closer and closer to pi. Using this method, after adding the first 10 terms, we have an answer of 3.0418. Well, that's not very good. How about 1,000 terms? Now we get 3.1405. Better, but still not great. In fact, using the Leibniz formula, we'd need to add millions of terms together to get just a few correct decimal places. This wasn't good enough for Ramanujan, and so he came up with his own formula. What's remarkable about this expression is that by adding just one term, you correctly calculate the first 8 digits of pi, which is better than the estimate we got from Leibniz's formula when we added 1,000,000 terms. The result is so good that looking at the graph from earlier, Ramanujan's estimate immediately sits right on top of the true value of pi at this scale. You'd have to zoom way in to even see the difference. Somehow, Ramanujan derived a formula for pi so powerful that even decades later, it was still used to correctly calculate millions of digits of pi. And that's just one part of his legacy. Other formulas have found surprising applications in modern physics, including areas like string theory.
Remarkably, part of his work is so deep and cryptic that mathematicians are still trying to understand it today.
We're huge fans of Veritasium. A while ago they published an amazing video on a special method Hardy, Littlewood, and Ramanujan came up with. Go check it out. Link is in the description. Hardy sees Ramanujan's talent and wants to help him publish parts of his work, but he also knows it needs a lot of polishing, improving the English, refining the notation, shaping the results. So Hardy steps in as Ramanujan's editor. In 1914, Ramanujan publishes his first paper in England, a study on approximations of pi. It's work he began back in India, and he likely could have gone on publishing directly from the notebooks. But over time, Hardy encourages him to go further. He wants Ramanujan to create new mathematics, using new methods he's teaching him. So for now, Ramanujan sets the notebooks aside. Hardy's guidance sparks new enthusiasm in Ramanujan. Just a year later, he publishes 9 papers. One of them focuses on what he calls highly composite numbers, numbers with more divisors than any smaller number. Hardy praises the extraordinary insight Ramanujan shows in the work. One day, Ramanujan tries to explain the concept to a student and another mathematician. As he flips quickly through the pages, sharing idea after idea, the mathematician struggles to keep up and ends up with a splitting headache. Ramanujan is happy. His scholarship pays well, nearly 4 times the annual salary of an English industrial worker at the time, and he has something just as valuable as the money, the freedom to focus entirely on his mathematics. Ramanujan goes on to publish one remarkable paper after another, with Hardy helping to polish the proofs and sharpen the presentation. They even collaborate on projects. But at the same time, life is growing more difficult for Ramanujan. Ramanujan is in England at one of the worst possible times. In 1914, World War I breaks out. It marks the beginning of a dark chapter for Europe, and for England. Ramanujan feels the impact as most students head off to war. Many won't return. Even Littlewood, with whom Ramanujan had grown close, leaves to contribute to the war effort. In the years that follow, Ramanujan becomes increasingly isolated. He withdraws, rarely leaves his room, and often works through the night. On top of that, the English climate is harsh, especially for someone from South India, where it's never cold. One cold winter's day, in 1914, a student visits Ramanujan in his room at Trinity College, where he's now living. The room is freezing, and Ramanujan sits close to the fire. He tells his visitor it's been so cold, he's had to sleep in his overcoat, wrapped in a scarf. Concerned, the student checks to see if Ramanujan has enough blankets. He finds them neatly folded and tucked away in the bed. And then it hits him. Ramanujan doesn't know how to use them. When the student shows him how, Ramanujan is deeply grateful. The war makes it harder for Ramanujan to follow his caste rules around food. Before leaving India, he had promised his mother to stick to them, only vegetarian meals, prepared and eaten in the presence of Brahmins. So Ramanujan mostly cooks for himself, simple things like rice, yogurt, and fruit. But as the war drags on, ingredients become scarce, prices increase. Eventually he survives on little more than rice with salt and lemon juice. Without proper nutrition, his health begins to deteriorate. Through these difficult years, Ramanujan's relationship with Hardy becomes his anchor. Hardy turns into the best friend Ramanujan ever had, and seeing his immense potential, Hardy pushes him, hard. He wants Ramanujan to go further, to reach the full limits of his genius. Ramanujan in turn becomes addicted to Hardy's praise. He wants to live up to it, to prove himself worthy. But that pressure only deepens the strain. Unlike back home, there's no one here to remind him to rest, no one to cook while he works, no one to comfort him as his isolation and suffering grow. His passion for mathematics, and even his bond with Hardy, can't fill those gaps. By 1917, Ramanujan becomes seriously ill. It's never clear what exactly he suffered from. Some say tuberculosis, others suspect it's an intestinal disease. Probably the missing nutrients were taking their toll. When Hardy learns of this, he writes a letter to the university in Madras, stating that Ramanujan is suffering from an incurable disease. Ramanujan is sent to a nursing home, but even while sick, he isn't an easy patient. He stays picky about food, constantly complains about his aching body, and doesn't believe in medicine. Even Hardy admits,
"It is very difficult to get him to take proper care of himself."
Over the next 2 years, Ramanujan sees multiple doctors and spends time in at least 4 different hospitals and sanatoriums. During this time, letters from his family and even from his wife become fewer and farther between. The silence weighs on him, and he becomes more and more depressed, until one day he simply can't take it anymore. Ramanujan stands alone on the platform of a London Underground station. A train approaches, and Ramanujan throws himself onto the tracks. A guard sees what's happening. He rushes over and pulls the emergency switch. The train screeches and comes to a halt just a few feet in front of Ramanujan. Policemen drag him out of the station. At the time, attempted suicide is considered a crime in England. Ramanujan is arrested and brought to Scotland Yard. Hardy gets called to the police station, and he uses all his charm and academic status to assure the policeman this person is no criminal, but an absolute genius. So they decide to let him go. The officer in charge later admits that they didn't want to ruin his life. Ramanujan returns to another nursing home. Then, in February 1918, he receives a telegram from Hardy, with news so unexpected he can hardly believe it. Ramanujan has been elected a Fellow of the Royal Society, one of the youngest in history. It's among the highest honors in science, reserved for those with truly exceptional insight. Past fellows include names like Isaac Newton and Charles Darwin. Ramanujan is thrilled. He writes back to Hardy, saying his words aren't enough to express his gratitude. But Ramanujan is still seriously ill, now undergoing treatment for tuberculosis. He suffers from high fevers and unexplained pain. While still in the nursing home, Ramanujan receives news from Madras. He's been offered a fellowship, £250 a year. It means he could return home to India and even come back to England occasionally for research. By now, Ramanujan has likely had enough of Europe. He accepts the offer and leaves Hardy in Cambridge behind, a place that gave him so much, but also left deep scars. Ramanujan arrives in Bombay. His mother is there to welcome him. Back in Madras, Ramanujan finally reunites with his wife. She'd been 13 when he left. Now she is 18. When the secretary of the Indian Mathematical Society sees Ramanujan in Madras, he is shocked. He looks awful, he lost weight, and his character changed. He isn't cheerful and affectionate anymore, but depressed and cold. Doctors advise Ramanujan to move somewhere cooler to support his recovery. So he relocates to a town near his birthplace, and later returns to the place where he spent most of his youth, Kumbakonam. This time, his wife is with him. Doctors visit him, examine him, treat him, but his health continues to decline. Through it all, he never stopped doing math. In January 1920, Ramanujan writes to Hardy one last time. He shares what he calls a new invention, Mach theta functions, and includes examples. These functions are extraordinary, mysterious, and for decades, no one will fully understand them. They would become his final legacy. By that time, Ramanujan is just skin and bones. The pain is constant and intense. His wife tends to him, placing hot towels on his legs and chest, trying to ease the suffering. Even then, 4 days before his death, he still writes about math.
All I can tell you is that day and night he worked on sums. He didn't do anything else. He wasn't interested in anything else, just sums. He wouldn't stop work even to eat. We had to make rice balls for him and place them in the palm of his hand. Isn't that extraordinary?
On April 26, 1920, Ramanujan falls unconscious. His wife sits by his side, gently trying to feed him diluted milk. By mid-morning, he passes. He's just 32 years old.
For him, in this universe, maths was everything. On his deathbed, he told me that his name would live for 100 years.
A merchant ship is on its way to Rome. It is loaded to the brim with treasure. Just past Crete, it gets into a heavy storm. The 300 tons of cargo make it very heavy, possibly too heavy. The ship sinks. History became legend, legend became myth, and for over 2,000 years, the ship passed out of all knowledge. Perhaps it would have been forgotten forever, swallowed by the sea like so many ships before it. That was until a sponge diver from a small town of Simi makes a dive into the ocean. On the sea floor, he discovers a bronze hand sticking out of the mud, heavily corroded, but still recognizable. He reports his findings to his captain. With the help of the Greek government, the crew recovers what must have been a shipwreck. Ancient bronze and marble statues, fragmented pots and vases. It's the largest collection of Greek artifacts ever found. They take everything to Athens. Museum staff are piecing together the artifacts. Meanwhile, this corroded lump of bronze still sits there, unnoticed. Over the course of the next few months, it dries up and cracks open. The shattered rock reveals something very strange. A large wheel, engraved letters, and a number of smaller gears. It looks like an ancient machine, a sophisticated device that simply should not exist, with a mechanism over 1,000 years ahead of its time. For over a century, archaeologists, engineers, and physicists from all over the world will try to solve the riddle of the world's first computer. This video is largely based on the fantastic book Decoding the Heavens by Joe Marchant. Link in the description. Greek archaeologist Valerios Stais is the first person to examine the strange objects. The many traces of gears lead him to believe that this must be some kind of ancient clock. But mechanical clocks were not invented until the Renaissance, 1,400 years later, and while there are mentions of toothed wheels, no gears from antiquity has ever been found before, at least until now. Stais soon realizes that he needs the expertise of others. He invites John Savorinos and Adolf Wilhelm, both experts in ancient text. They decipher the scribblings as ancient Greek letters. Another scientist named Pericles Podiatis studies the inscriptions and suggests that they must be operating instructions. This word in particular stands out to him. It's an old and unusual word for the zodiac scale, a scale dividing the year in 12 zodiac constellations. Podiatis and Savorinos conclude that the device must be an astrolabe, an ancient calculator to measure the position of stars and planets. But traditionally, astrolabes don't need gears. Maybe this strange astrolabe was somehow able to determine the position of stars mechanically. In the following years, the fragments are carefully cleaned. Albert Rehm, an expert from ancient languages from Germany, travels to Athens to inspect the device. He discovers another word previously hidden, an ancient Egyptian month in Greek letters. What if, Rehm argues, this machine is able to simulate the movement of celestial objects throughout the year? Shortly after his discovery, work on the Antikythera mechanism stalls. Years pass without any new major breakthroughs. 2 world wars hamper the excitement. The machine survives at the bottom of some storeroom crates, in danger of being forgotten again. Computer technology has come a long way. Today, we don't just study stars or track time mechanically. We can now access and control our most powerful tools from halfway across the world. This is possible because of services like our sponsor, AnyDesk. AnyDesk is a free, lightning-fast tool that lets you access all of your devices remotely. Whether you're making complex 3D animations on your laptop from the coast of Greece, or just helping a family member troubleshoot tech issues, AnyDesk is here to help with reliable and secure connections, even in low-bandwidth situations. The clean interface makes AnyDesk a breeze for anyone to use. It's available for all platforms, from your laptop into your phone, all the way to your grandmother's Windows XP machine. If the Antikythera mechanism would have had an internet connection, maybe it could have run AnyDesk as well. If you want to check out what AnyDesk has to offer, go to anydesk.com/fern and try it for free. Fast forward to 1953, a new generation of divers is in the waters near Antikythera. Among them, Jacques Cousteau, filmmaker and pioneer. Thanks to him, diving gear went from this to this. Divers can go much deeper now. There are many stories of treasures that fell over the cliff beneath the wreck site. They were out of reach for the sponge divers back then, but not for Cousteau and his crew. After days of searching, they find something buried under a thick layer of sand. the sunken ship's hull, almost perfectly preserved. But the crew does not have the necessary equipment to unearth it. They return 2 decades later with better gear and a camera. The crew finds more treasure, but no new parts from the mechanism. Luckily, science itself is developing rapidly. Derek Price, a historian from the UK, uses newly developed X-ray technology to scan the existing fragments. He finds more gears and is able to build the first model of the Antikythera mechanism. He calls it a calendar computer. But his model isn't very accurate. For it to work, Price had to change the number of teeth on the gears, despite his X-ray images showing otherwise. The researchers Michael Wright and Alan Bromley see that Price clearly made some mistakes, so they decide to solve the mechanism themselves. The two fly to Athens. For a month, they re-examine, measure, and photograph the 82 remaining pieces of the device. But after 2,000 years, and likely passing through as many hands, the inevitable happens. Maybe an X-ray was the right call, after all. The two learn of a relatively new technique called tomography. It basically works by taking multiple slices of pictures from an object and putting them together afterwards. They take a total of 700 images. With them, they can have a clearer look at the inside. After years of work, Wright and Bromley are this close to unraveling the mystery. But suddenly, Bromley cuts ties with Wright. He thanks Wright for his work, takes the images, and leaves. A few years later, Bromley is diagnosed with cancer. On his deathbed, he confesses to Wright he alone wanted to be known for solving the Antikythera mechanism, but he failed. In the end, Bromley hands over his 3D scans to Wright. Wright had already designed a prototype in 2002, but with these images, he would be finally able to solve the device. Or so he thought. Tony Freeth, a mathematician and filmmaker, gathers a group of researchers under the Antikythera Mechanism Research Project. The group scans and measures the fragments yet again, this time with even better and newer technology. The quality of their images is astonishing. Even the smallest inscriptions, hidden deep within the stone, are now readable in sharp detail. They regularly publish new papers of the device. There are a few more expeditions to the shipwreck, with drastically changed diving gear. But again, no one can find new pieces of the mechanism on the seabed. In 2021, Freeth and the others are finally able to put together all the pieces of the puzzle. They are able to combine all the evidence of the last century in one machine. The mystery of the world's oldest computer is finally solved. So, what does it do? A computer is a device that can store and process information. Any device that is able to solve math equations and show you the result can therefore technically be considered a computer. There are two types: digital computers, like the phone you're watching this video on, and analog ones. So you have this task, 8 times 2. Digital computers work with ones and zeros. To solve the task, the first is to translate the numbers in binary 1000 times 0010. One way to multiply the numbers would just be to multiply the individual numbers one by one and add the individual results, just like in school. Translate the number back to decimal, and there's your result. But there is also another way. The same task can be represented by an analog computer with gears. This can be translated into one gear with 8 teeth and a larger one with 16. Each time you turn the larger gear once, the smaller one turns twice. Mathematically speaking, the input has been multiplied by 2. This is basically what clocks do, transforming seconds into minutes and minutes into hours. And this is also what the Antikythera mechanism does, only that it's much more complex. The device originally sat in this wooden box. It had a handle on the side to control the complex internal mechanism. These gears move a series of pointers at the front and back. The ancient Greeks believed the Earth was at the center of the universe. That's why Earth sits right in the middle. Around it orbits the Moon, as well as the Sun and the 5 planets that were known at the time. There are also rings for the Egyptian months and dates with its respective zodiac. Additionally, the front is full, with step-by-step instructions on how to use it. The back shows 2 spiral rings with large pointers in the middle. The upper one shows the 19-year Metonic cycle. It's the basis for many ancient calendars. Inside these rings is a smaller scale showing the 4-year cycle of the Olympic Games. The lower ring is an eclipse predictor that, well, predicts eclipses. The Antikythera mechanism is a complex simulation of the cosmos. Take any day, the machine shows you where the moon stood, which star constellation was rising, or when the next eclipse was coming. All this in a wooden case as large as a book. Perhaps it was used by astronomers or by teachers. But one common theory suggests otherwise. It most likely wasn't a tool. It was probably a luxury toy. A very impressive and also very expensive piece of tech for anyone who can afford it. Some suggest it might have been used to cast horoscopes.